Hi, Algebra 2 students. Here we are in Chapter 12, and we're looking at Section 12.8, Binomial Experiments. So what we're going to discuss in this chapter, or in this section rather, is the idea that the binomial expansion theorem can be used to help determine certain types of probabilities, particularly by probabilities where there's only two possible outcomes and you know the probability of each of those outcomes individually. Let's give an example. So suppose you have this 5-question quiz, and the quiz was multiple choice with only one answer per quiz question, so A, B, C, or D. This would be a place where we could use the binomial expansion to figure out how many possible right answers you can get versus how many possible wrong answers you can get. And so what this section shows is that if you take right plus wrong and the fact that there's 5 different problems, raise it to the 5th power, this expansion will give us some real insights into the possibilities for the probabilities for different situations. So let's look at it deeply. So you'll remember that back in chapter 11, we had like Pascal's triangle, and we had the binomial expansion theorem to show how to multiply or to expand a binomial to a different power. And so what we can do is look at this as all the possible ways of different situations happening. Let R represent the number of ways for all the questions to be correct, or the number of correct questions, and let W represent all the wrong answers, the number of wrong answers you can get. So how can you get all 5 answers correct? Well, there's only one way to do that, right? The coefficient 1. How many ways is there to get 4 questions correct and 1 answer wrong? Well, you can do that in 5 different ways. How many ways is there to get 3 correct and 2 wrong? You got it, 10. And similarly for 2 right and 3 wrong, there's 10 different ways. So this is kind of neat, but why this gets really even cooler is if you think about the probability of each thing happening. So watch this. Let's say the probability of guessing the right answer, just like randomly guessing the right answer, would be 1 out of 4. And therefore the probability of getting the wrong answer would be 3 out of 4. I don't think anybody would argue with that. And so if we were to literally figure out the probability of getting, let's say the probability of getting 3 right and therefore 2 wrong, what we would do is we would go up to that particular term, 3 right and 2 wrong. Where is that? Right here. And we would plug in the probabilities and multiply by the coefficient in order to calculate the probability of that happening. So after substituting in 1/4 for the number right to the 3rd power and 3/4 for the probability of just guessing it wrong, my calculations come to like 30 over 1024, which can be reduced, but this will be the probability of this situation happening. That's kind of neat, right? And so like the probability of getting everything wrong would be this, probability of getting everything right. Kind of neat. I don't know if you guys like it, but we'll do 2 extra examples so we get a little bit more practice. All right, let's consider a family that has 4 children. What is the probability that they have 3 boys and 1 girl? The first thing we need to kind of consider is what is the situation that we're dealing with and how does it relate to a binomial expansion? Probability of getting a boy plus girl, and we are dealing with a 4-member family, or 4 children. So we would consider the expansion as it follows like this, right? And you guys remember all of this from chapter 11, how we can expand binomials. And so I'm just going to go through and write this down and know that you all know how to do it. So then this matches the probabilistic situation. So now we got to think about the true probabilities. In general, the probability of a boy is 1/2, and the probability of a girl would be 1/2. So if I wanted to know the probability of having 4 children, all of these situations represent that, and having 3 boys and 1 girl, I would come over here and say, okay, well, there's 4 ways to have 3 boys and 1 girl, if you think about that, right? in terms of order, birth order, it could be girl, then boys after. The girl could be second, the girl could be the third child, or the girl could be the last child. So that's what that 4 is indicating. There's 4 different scenarios that would work in this way. And so now with that notion, we also need to consider what the probability is. So it's going to be 4 times 1/2 to the 3rd power times 1/2. And when we calculate that, we end up with 4/16 or 1/4 of a chance of that occurring, 25% there. So some key concepts we want to keep in mind. A binomial experiment exists if and only if these conditions occur. There must be exactly 2 possible outcomes and no more, no less. There is a fixed number of trials. So we're talking about 4 children, 5 children, 7 questions on a test or whatever. The trials are independent. One does not affect the other. And the probabilities for each trial are the same. So in each circumstance, whether it's 3 boys or 2 boys or 1 boy or whatever, or 5 test questions or 20 test questions, the same probability will be consistent. So here's our last example. Suppose that when hockey star Jaromir Jagr, sorry if I got that name wrong, guys, takes a shot, he has a 1 out of 7 probability of scoring a goal. He takes 6 shots in 1 game. What is the probability that he will score exactly 2 goals? So let's think about what this means. He can either score or not score. And so we will write S will stand for score and not score will be the other circumstance. We know he's going to take 6 shots. So that's 6 different situations. And I'm going to expand that. Or I could even just pull up the binomial expansion theorem and go to the specific term that I'm concerned about. And I think we'll do that because we already did expanding in the other examples. So if we're thinking about this, we're really thinking about the probability of 2 goals. And so if we want the probability of 2 goals, what we're thinking about is the term where we have 6 choose 2, right? 6 different options and we want to choose 2. So that would be the coefficient that we're dealing with. And we know that that would be S, kind of like S to the 2nd power and N to the 4th power. So once we calculate 6 choose 2, we get 30 over 2. And then we remember that the probability of him actually scoring was 1 out of 7. So that's 1 out of 7 squared. And then the probability of him not scoring would be obviously 6 out of 7 to the 4th power. When we calculate that, we end up with a ginormous number, 19,440. Of course, I'm expecting you to use a calculator here, and over 117,649. And so that's approximately 0.17 would be the probability for this event to occur. And finally, what is the probability that he will score at least 2 goals? And so when we read at least, we know that anything above that is fine. So in a sense, we want to know what's the probability of him scoring 2, 3, 4, 5, and 6 goals, right? So that's a lot to calculate. We can calculate that and add up those different probabilities, or we can think about the probability of him scoring none and 1 and separate that from 1, from like the number 1, which would be like absolutely this will occur. So this is the route we're going to do because there's a fewer calculations. So specifically, it should look like this. The probability of at least 2 goals is 1 minus the probability of no goals minus the probability of 1 goal. And so how do we calculate this? Well, 1 is what it is. And is what it is. I don't need an equal sign there. 1. And then the probability of no goals would be C choose 6 choose 0, right? There's only one way for that to happen. And then that means if no goals are chosen, let me write this better. Let me try that again. So if you are not scoring anything, that means that's going to be S to the 0 power and n not scoring to the sixth power, right? So all of them will be misses and there will be no scores. And so that's the coefficient for that would be 6, choose 0. And then the coefficient for only making one goal would be scoring once, not scoring 5 times, and then it would be, the coefficient would be 6, choose 1. And so now we get to calculate that and also include in that the probabilities. So 6, choose 0, the only way for that to happen is for that to be 6. Yeah, no, that's 1 actually. Yeah, that's 1. I'm sorry, guys. And then as to the 0 power, well, that would be 1/7 to the 0 power, and then 6/7. That's the probability of not scoring to the 6th power, minus, I think we're on a roll out. We're getting it. 6, choose 1. There's 6 ways to do that. So the coefficient is 6. Again, scoring was a 1/7 probability, and then not scoring is 6/7, and then we'll raise that to the 5th power. So we'll calculate that, and we end up with this first one, there's 46,656 different ways for that to occur out of 117,649, and then we're going to subtract from that also 46,600 and I'm going off. 46,000, again, it's going to be the same probability actually. 46,656, again, over 117 times 117,649. And once we do that subtraction, let me get a little bit more space before we get to our next lesson, we get 24,337 out of 117,649. And that's going to be approximately 0.21. So a whole lot of calculator work on that last one. And that is indeed our last example for this section. Let me know if it made any sense. Let me know if there's any challenges to doing it. And I know it's going to require us to do a little bit of review of that binomial expansion theorem to get our assignment done. Hopefully it's not too onerous. Look forward to talking to you guys soon. Take care. Bye-bye.